Okay, so far what we have done is we have gone through and we have listed all of the fluxes of water, energy, and carbon that enter and leave our idealized land system through the top and through the bottom. We have then derived budget equations for each of those that express the rate of change of water, energy, and carbon as a function of the inputs and outputs, the difference of those fluxes that we listed. So what I'd like to do now is just bring up a summary slide of all of those budget equations that we derived. And I'm going to go through each one and just sort of recapitulate what we found for each of those equations. And so here is our water equation. Again, what it says is that the change in water storage, the change in soil moisture with respect to time, is just equal to the precipitation coming in, which is the only input of water to our system. And it's balanced by the evapotranspiration going out, the recharge, which is lost from our soil system to the deeper groundwater, and the runoff that leaves our land surface and ultimately goes to rivers and streams and ultimately out to the ocean. So that is our water budget equation. Okay? So our energy budget equation says that the rate of change of heat storage, and so the important thing here is that the heat capacity of the soil we're assuming is constant. So we can take it out of this derivative. Okay, so what this says is that the rate of change of the soil temperature with respect of time is equal to the net radiation, which is sort of the input of radiation, the net of the incoming solar and long wave and outgoing solar and long wave radiation fluxes. So that net radiation flux term here is the input. We have a loss of energy in the form of ground heat flux from the near surface to the deeper surface. We have a loss of energy from the system that represents the latent heat flux, the energy associated with the evaporation and transpiration of water from our land surface out to the atmosphere. And what we're saying here, importantly, is that latent heat flux is just equal to the latent heat of vaporization of water, of liquid water, times the rate of evapotranspiration. So this should look very familiar from your properties of water lab early in the semester. Okay, so important here to recognize that loss of water is also resulting in a release of heat from the land surface to the atmosphere. Okay, and then ultimately we also lose energy from the land surface in the form of sensible heat flux. So that's our energy budget equation. Finally, if we go to our carbon budget equation, what we see is that on the left-hand side of the equation, we have the rate of change in ecosystem carbon with respect to time, and that is equal to, on the input side of the ledger, we again have the carbon acquired through photosynthesis. And again, we're assuming here that this is just some constant times our rate of evapotranspiration, right? And what this recognizes is a relatively simplistic, but a first order guess that the plants are releasing water, that one of the reasons that they transpire is to simply gain carbon, right? So their stomata open, water leave through those stomata, and in exchange they get some amount of carbon dioxide, which they can then fix into carbohydrates for food. Okay, so that's the input term. On the output side of the ledger, we have respiration from plants, we have respiration from the soil environment, and we have loss of carbon through dissolved fluxes, carbon that dissolves into soil water, that percolates down and is lost from our system. Okay, so those are our three budget equations for water, energy, and carbon. And the thing that I think is absolutely fascinating about these equations, and the reason why I call this lecture The Beauty of the Coupled Water, Energy, and Carbon Cycles, is that if we take a look at this variable, evapotranspiration, appears in all three of these equations, right? So we have a loss of water from the terrestrial system in the form of evapotranspiration that also represents a loss of latent heat from the land surface, so the energy associated with evaporating that water from plants and from the soil. And we also have it appearing in our carbon budget equation, in which it represents a gain. So the carbon is acquired through evapotranspiration. So this, for me, when I first saw it, was a really kind of cathartic moment in my experience as an eco-hydrologist. And I will always sort of remember the set of lectures that we went through to arrive at this result. But what this sort of, the takeaway message here, right, is that anywhere you go on the land surface, any vegetated location, that the water, energy, and carbon cycles are intimately coupled through this evapotranspiration flux, right? So, and if we think more about that in sort of natural ecosystems, what this tells us is that plants actually play an extremely important role in the Earth system by connecting, by linking these global water, energy, and carbon cycles. And so when we go and we think about where we're at and the other places in the world, going forward from this class, right, we've spent a lot of time asking sort of the essential question that we asked at the very beginning of the class, right, is why is the West dry like it is, right? And how does that differ from places, for instance, in the Arctic and in the tropical rainforests, right? So why in the West do we tend to have, drier conditions, less vegetation? And one of the things that I'd really like you to take away from this class and from this set of lectures is just the understanding that, all of those things, water, energy, and carbon, go together in all of these landscapes. And I'd really like you to reflect on and think about what the factors are that control evapotranspiration in all of these environments, and how that ultimately influences the cycling of water, energy, and carbon, both now and how that might change in a warmer future, or in a future in which the precipitation regimes might change. So thank you for listening through this set of lectures. I hope that you have an appreciation, or that this was helpful for you like it was helpful for me when I was a student. And I have really enjoyed taking you through this journey in the class, and I wish you the best of luck as hydrologists in the future.